Well, the first thing you should know is that we've combined section 4-6 and 4-7 from this particular book. Most books it probably wouldn't represent too much of a combination. There's one section that says using congruent triangles, and the other one says using isosceles and equilateral triangles. And there's not really that much content in using congruent triangles to warrant a whole separate video. So I put them together. It's not that much you have to know. There's a phrase that's very common, well, sort of common, especially if you're texting proofs back and forth. It goes like this: C, P, C, T, C. Yeah, doesn't look like much, does it? What it means is corresponding parts of congruent triangles are congruent. Now, we actually use this without just saying it. Well, we sort of said it, but we didn't write it out in this nifty little shorthand. The other day we worked out a problem that required us to show two triangles were congruent, and we showed two other triangles were congruent, and the whole idea was to show that two separate angles were congruent. So we showed these two triangles congruent, and then we showed a couple of bigger triangles were congruent, and then used the fact that since the larger triangles were congruent, we just matched up the angles and said they had to be congruent also, because that's the definition of congruent triangles. They have congruent sides and congruent angles. Well, this is just a shorthand way of saying that, that's all. It's no big deal. We used it. We've been using it all along. This is just a shorthand way of saying it, that's all. It's not really a big deal. But when you see that, don't get confused. It looks like a mess, but it just stands for the fact. And that's all it is, just a simple little fact that corresponding parts of congruent triangles are congruent. Now, how do you use congruent triangles? Well, you could probably think of a few things, but let's try measuring the distance across a river. I know that sounds kind of weird. What in the world would a congruent triangle have to do with the distance across a river? Yeah, suppose you got some part of a river here. It's a big river. You can't just run your steel tape across it. Surveyors call it a chain. It's just sort of a steel tape on a spool, has a handle. If you walk away with it, it unravels, and you can ravel it back up with the handle on the reel, kind of like a fishing rod, except, a fishing reel, but much bigger. Suppose you want to know how far it is from here to here. And normally, when you're surveying and computing distances, you run your steel tape out and you drive a stake, and then you run it out some more and drive another stake, and you just keep adding up the distances between stakes. Well, I don't think you have to be a professional surveyor to figure out that driving a stake into a river is a problem. So what can you do? Well, we're going to measure it indirectly. And in this case, since there's a bend right here, maybe I should have put the bend the other way, but this just shows you that it can be done even when it's confusing. We put a stake here. We run this straight line out, and this is the distance that we want between these two stakes. We just continue with this straight line so that we can drop a perpendicular down. We draw another straight line here, perpendicular to this one. Now we take our equipment, and this can be done fairly easily with surveying equipment. We find the midpoint of this, and then we run a line from this side of the river like this. When I say run a line, what I really mean is we have equipment that's going to allow us to produce a direct sight line around here. We don't necessarily have to actually run string right across the river all the way down here. We just take our transit and shoot a straight line from here to here. And in reality what you would do is you'd stand right here. You'd take your transit, if you're using that old style type surveying equipment. Most people use lasers now, it's probably a lot easier. When you have this line, then you just flip it around 180 degrees and shoot this way. And there's another guy who will walk out with a stake to the right spot. You can tell him when he's all lined up and he can drive a stake. Then you draw a perpendicular line here. These two lines, this one we drew from the stake and this one perpendicular to this, they will intersect. And when that happens, what do we have? Well, we have a triangle here. And we have a triangle here. Are they related? Oh, yes indeed. The fact that we used right angles really helps a lot, because these two lines, this line and this line, are perpendicular to a third line. Two lines that are perpendicular to the same line are parallel to each other. Remember that? Since these lines are parallel, this is a transversal cutting these two parallel lines. So we have interior angles here. This angle and this angle are congruent. Now we get to why we use the midpoint here, which doesn't look that much like a midpoint, but take my word for it, that's a midpoint. This side is congruent to this side. So what do we have? We've got an angle congruent to an angle, another angle congruent to this angle, and a side congruent to a side. So we have our angle-side theorem, which tells us these two triangles are congruent. What good does that do? Well, if we measure this side, which we can do, this is on the ground, this is on solid ground, so we can take our steel tape and with a couple of guys and a set of stakes, if this turns out to be 500 feet, we can measure it as 500 feet. But congruent parts, congruent triangles are congruent, which means this line, side, must be congruent to this side. If this were 500 feet, that means from here to here is 500 feet. Now this is on solid ground, so you'd actually have to measure the distance from here to the riverbank and subtract that from the 500 to get the actual distance across the river. Why? Well, it's because there's a bend in the river. If we were over on this side of the river and did the same thing, we could drop a line straight down from the bank here and not have this little extra piece we'd have to subtract out. But this is the basic idea of how you could use a congruent triangle to figure out how far it is across something that you could never drive a stake into. This could also be like a canyon where you can't drive stakes into midair. So, same problem. As I said, we'll do a lot more of this sort of thing in a couple of sections a couple of chapters actually, when we study similar triangles. This is an indirect measurement. We're figuring out what this is by measuring this down here. We're not actually measuring this. We're measuring this and using our properties of congruent triangles to demonstrate that these are the same. We can measure this just as well as this and get the same measurement. But with similar triangles, we can do a whole bunch of different things, measuring things indirectly, especially heights, which is something that's very high. It's also hard to measure, but we can do it indirectly. There's a couple of useful theorems. In fact, I almost used this theorem in that same problem There was a demonstration of corresponding parts of congruent triangles are congruent. Again, with this problem, once we determined that these two triangles were congruent, I could put those double hash marks in there and started to point out that these two angles have to be equal because it's an isosceles triangle. But I had to stop myself because we didn't know that yet. We could go back and do this and maybe save ourselves one step. Because once we found that this was 70, then we would know from this theorem here that this was 70. But back when we were doing this problem, we didn't have this theorem, so I couldn't use it. Bummer. As you can see, this is probably not a big surprise to you. If these two sides are congruent, then it'll turn out that these two angles are also congruent. So that an isosceles triangle, which has two congruent sides, will also have two congruent angles. And conversely, if you end up with two congruent angles, like this shows here, then you have an isosceles triangle. So it goes both ways, in other words. This here, this then angle, and then if this angles are congruent, then, well, we could change both of these now that we have both of these theorems into one of these, couldn't we? Goes both ways. And this will be useful and probably easy to remember. It kind of makes sense. It's pretty much what you'd expect, isn't it? There's some more of those corollaries. Basically theorems that just follow very easily and directly from another theorem. Why would this follow easily and directly from this? Well, if we have three congruent sides, then we certainly have two, don't we? So, for the moment, forget this as an equilateral, think of it as an isosceles. Let's say these two are our congruent sides, then these two angles must be congruent. But now let's consider this side and this side. That makes this an isosceles triangle with these two base angles. And they have to be congruent. Wait a minute. We just had that these two are congruent. Now these two are congruent. So we got C is congruent to B, A is congruent to B. Well, we got transitivity that tells us A must be congruent to C. So they're all congruent to each other. And of course it goes the other way too. But you can see what you're doing here. You're really just applying the base angles theorem for isosceles triangles twice, because all three sides are congruent. So you could pick these two to be the congruent sides, and then pick these two to be the congruent sides. So that's all this says here. Since two sides are congruent, then their opposite angles are congruent. Well, in an equilateral triangle, we have at least two congruent sides. So maybe I should have said this is not say if we have an isosceles and only if we have an isosceles triangle. It just says that we have to have at least two sides that are congruent. Having three sides that are congruent, base angles theorem and the converse will still both hold. Maybe I've over-explained this, sorry. Well, here we have another example of a guy making geometry videos who messed up. What did he do? Well, let's see here. Angle A is congruent to angle C. Okay. Okay, that's in the diagram. So our converse to the base angles theorem should tell us that the two opposite sides are congruent. That would be AB and BC. And he's got that here. He's got BC and, oh, wait a minute. That's not right. He used AC. No, it's got to be the opposite. This side's opposite this angle, this side's opposite this angle. It's AB and BC that are congruent. Okay, in this problem we've got two congruent angles. Well, this is definitely a job for our converse base angles theorem. These two sides must be congruent. So we just set up our algebraic equation again. Subtract 4 from each side. And there it is, x equals 6. This one was pretty easy. You just had to spot the fact that these two sides are congruent. Then set up the equality. Very easy. Okay, and what we need to do here is, of course, find the values of x and y. So we can treat this, well, kind of like a fill in the blanks, maybe. Let's see if there's anything we can figure out right off the bat. Jeepers, not too much. Well, let's see here. Let's call this angle down here if this is alpha, then this angle over here, it would also be alpha. Why? Well, these two sides are congruent, so the opposite angles are congruent. So whatever this is, it's congruent to this. And we can say that here also. If this is x, then this is also x here. And that's because these two sides are congruent. Now what we have here is a 90-degree angle. So if we figure out what alpha is, this angle here will be 90 minus alpha. These two are supplementary. This is a straight angle here. So one relationship we can set up right away is that y plus x equals 180. Those alphas didn't look too good to me. I think maybe we should put everything in terms of x and y. For instance, we have y plus x equals 180. We also know this angle here is 180 minus 2x. That might help us later. That would be this one here. I didn't want you to have to sit around watching me do too much of this algebraic stuff. I went ahead and wrote it in, and now I'll explain it to you. I think we previously figured out this much. These two angles have to be congruent because of the congruence of these two sides here. And same thing here, these two have to be congruent. I initially wanted to put in alphas here and thought, no, that's no good. Let's try to get everything in terms of x. In fact, this angle here is 180 minus 2x, right? Has to add up to 180. We got 2x's here, so whatever x is, this angle here, this is the small one, not the right angle. Now this it's a 90-degree angle, that this is 180 minus 2x, then this must be, what's left here must be 90 minus this, which is 180 minus 2x. So that's what I wrote down here. And then rearranged it, of course. So we've got 2x minus 90. That's an expression for this angle here in terms of x. And this angle is equal, congruent to this angle, because these two sides are congruent. Okay, now we have some relationships set up. Actually, we have the angles drawn in terms of x. Now we can start setting up some relationships. For instance, I think we already wrote in that y plus x is 180 because this is a straight angle. That part's pretty easy. And it starts getting kind of messy in here now, because what else equals 180? Well, this angle plus this angle plus this angle would be 180, wouldn't it? But that's 2x minus 90 plus 2x minus 90. 2 times 2x minus 90 plus y. And we write it all out. Add 180 to each side. Subtract 4x, and we get y equals this stuff here. Now what we have is y in terms of x. Here we've got y plus x equals something. Here we've got y and x equal to something else. Naturally, we have to try to get rid of one of the variables so we can solve one equation in one variable. That's what we do here. We can just put that back in here. X plus y, which is 360 minus 4x, equals 180. We solve that and we get 60 for x. That means it turns out that this here, the smaller angle, is 60 degrees. They're all going to be 60 because they're all x. So this is actually an equilateral triangle. So it turns out we just figured out that this side is congruent to this side. What else? Well, now that we've got x, we can put y in here. Or pardon me, we can put x in here and get the y equals 120, which is what we've got down here. That actually makes sense. No, it was kind of long, but it's not that bad. The important thing was to recognize, which I didn't do at first, that we want to get every one of these angles in terms of x. That way you got something. When I first wrote an alpha in here and an alpha in here, I could start setting up equations, but then I just throw in an extra variable. I've got an x, I got a y, and now I got an alpha to figure out too. That's not the smart way to do it. The smart thing is to get these angles here in terms of one of your variables, rather than adding more and more variables and making the equation even more insoluble. Actually, that's probably not a thing, is it? It's either insoluble or it isn't. It can't be more insoluble, I don't think. Now here's an interesting one. Kind of. It's a triangle made of triangles. Another triangle made of even more triangles. If we create triangles this way from other triangles and start with one equilateral triangle, first question, how do you know these other triangles are equilateral? Well, the fact that each component is equilateral is going to help. For instance, this is one side of an equilateral triangle. This is another side of a congruent equilateral triangle, which means these two sides are congruent. It also means the same reasoning. This side is congruent to this side. This side is congruent to this side. This side is congruent to this side. So what do we have? Well, we end up with this whole thing. If we call this a side, this is an abbreviated s. This would be 2s. This would be 2s. And this would be 2s. Here, same thing. if one side of the equilateral triangle we just designate as S, because they're all the same, and we have S, 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 it's 3S this side, 3S here, and 3S here. The sides are all congruent, and we know from our side, side, side postulate, that means the angles are all congruent, and we have a equilateral triangle. Pardon me, an equilateral triangle. And the same thing here, it just keeps going up, up, up. You still end up with equilateral triangles. At each point, all you're doing is adding 1 to the length of each side. I mean, I'm treating the side of this equilateral triangle as 1 unit, whatever that happens to be. If that's 1.6 inches, then we'll just call that a unit. We'll call that an S unit. Each of these is an S unit. Here we got 2 S units, 3 S units, 4 S units. So as we build, they continue to be equilateral. Now, find the areas. Well, that's kind of obvious. You just count. They're each 1. So that one's 4. Okay. What about this one here? We got using the darker and lighter colors helps, I think. We got 3 of the dark ones here, and five. So if I counted right, I get about 9 here. What about this one? Well, I counted up and got 16 here. So what pattern do we see here? Well, if we label this one number 1, 2, 3, and 4, anything jump out at you here? 2 goes to 4, 3 goes to 9, 4 goes to, oh, well, if we label this generally I, then it looks to me like the area down here, if this is I, this is I squared. So, for the 7th triangle, should be 49, right? 7 squared. We didn't prove anything. We're just spotting a pattern here. And you did that because you're human, and humans are good at spotting patterns. That's not actually a proof. Proof would be a lot more complicated. But spotting the pattern, well, like I said a long time ago, it may be difficult to prove that dogs bark, but when you run across enough dogs and seen them bark, you recognize the pattern without a proof, and you're not surprised when the next dog you see barks. Here's one where I'm pretty sure we're going to use our base angles. There. Let's see here. We've got an isosceles right triangle. I drew it in here. And they're telling us it's isosceles, so these 2 legs are congruent. QR is the hypotenuse. Okay, looks like we drew it right. Find the angles P, Q, and R. Well, this is going to be kind of easy, I think. Why? Well, we know this is a 90-degree angle, right? Okay. We know that these 2 are equal, so we don't know what they are. We know that they're X. And we know that this here, this is 90. Well, that looks more like a curve than a right angle, doesn't it? Sort of. So can we find all of these angles? Oh, definitely. All we have to do is write that 2x plus 90 equals 180. Or 2x equals 180. Pardon me. 2x equals 90. Or x equals 4d 55. So this is a 45, 45, 90 right triangle. And you can see why it had to be 45. We got 90 degrees left over. These two have to be congruent, so we have to split up that 90 equally. We cut 90 in half and get 45. That's all we had to do. But it's not a bad thing to remember this. If both legs are congruent, then these two angles are going to be 45 degrees. It's a very common form of triangle, and it'll come up a lot in problems in the future. And right triangles will keep coming up and up and up because they're very important. I think I mentioned before, supports are usually 90-degree angles that keeps the force from, if you've got a table, if you got a leg bent in like that and the force is straight, the leg tends to bend up that way, doesn't it? And you got a broken table. Same thing if it went out. But when it's straight, that's pretty good support. Also, what else do we use 90-degree angles for? What about stacking? You notice that boxes are hardly ever round. It's not easy to stack round boxes, is it? Even if you manage to do it, it's really a lot of wasted space. Suppose you don't have to stack them, you just lay them out on the floor. There's still tons of wasted space. For instance, look at the difference when you're storing watermelons or rectangular boxes. Watermelons, you waste a lot of space storing watermelons, don't you? Well, somebody tried to fix that, in fact. I think it was in Japan. There's genetically engineering watermelons to be rectangular, sometimes even cubical, so that they stack easy and fit better in your fridge. I'm not kidding. That's for real. I read about it somewhere. I forget where. Now we're going to use this diagram to answer the question. Is P parallel to Q? Well, this won't be too tough. We have one of those straight angles again. So 130 plus what equals 180? I would say 50. So this angle here is 50 degrees. Well, these two sides are congruent, which means the opposite angles are congruent, so this is also 50 right here. Okay, so far so good. Now these here, these are corresponding angles, aren't they? And we have, well, 50 degrees here and 45 degrees here. I would say P is not parallel to Q. You see, two parallel lines cut by a transversal, corresponding angles are congruent. And the converse is also true. If corresponding angles are congruent, then the lines are parallel. But the corresponding angles are not congruent. So that's no-go. These two lines are not parallel. Here's one that sounds kind of weird, but it's probably not that tough. They're just asking you to find values. And they don't say, yeah, it says values here, right? Not value singular, but value is t. We may end up with more than one value of t, which works because it doesn't have to be equilateral. It has to be isosceles. So we can like set these two sides equal and see what happens. We can set these two, or we can set these two. If all three of those have solutions, then we have three possibilities for t. Let's see what happens. We'll try 3t equals 5t minus 12. Subtract 3t from each side, add 12, and we get 2t equals 12. Or t equals 6. Well, that's 1. That was setting these two equal. So we could have one isosceles triangle where t equals 6. And down here this would have a side of 26, so that's okay. We only need these two to be, and that would be, let's see, that's 18 and that's 30 minus 12, and that's 18. So that works. Suppose we set these two equal. What do we get? 5t minus 12 equals t plus 20. Add 12 to each side and subtract t. And we get 4t equals 32, or t equals 8. Okay, that one worked. What about this? We'll set t plus 20 equal to 3t. Subtract, and we get 2t equals 20, or t equals 10. So 6, 8, and 10 were your possibilities here. See, it looks at what they call it a challenge. You get all this stuff here that you're trying to visualize this triangle with all those t's around it. Well, don't make it hard on yourself. Just draw yourself a triangle. Push this stuff in here. And now it's easy to see what they're saying. They're saying set this equal to this, set this equal to this, and set this equal to this. And if either one of these, if any one of them doesn't work, then there might have only, it's possible there was only 2 values of t that would work. It's possible there was only 1 value of t that would work. They gave us one where the way these equations are set up, we could pick any 2 and make them congruent. Well, that's about it for now.